let's say, optimization algorithm, I should say. And we have own calculation codes and so on. So the quantum computing, for us, is the next steps. How we can continue to follow the state of the art in terms of computational power, and how we can also meet with some constraints in terms of cost, calculation cost, in fact, including energy. And that's why we would like to know whether a quantum computer can be competitive in terms of energy as compared to what we do with HPC.
And then you engage in this OECQ project, which Ariane described very quickly, because our work is part of that project. So explain why you were embedded in this project.
And so, yes, the OECQ project was the opportunity to meet the design of a quantum computer in terms of an energy perspective to the current performance in terms of energy of HPC. As we operate an HPC, we can use some tools. Some of these tools have been made here in Barcelona. And so we can run some real industrial calculation from end to end and have some metrics to show to the quantum community that today we can solve our industrial problem like that with such amount of energy.
I have a stupid question. You are an energy utility. Don't you have energy for free within the company?
Not, no. For our internal purposes, we pay our bill.
You pay the same price as anybody.
We pay the same price as the market price.
That's why you're motivated to have cheap power solutions. Okay. Thanks, Etienne. Cécile, as a vice president of QUIC, you know everybody in Europe. And by the way, Cécile has been very helpful in pushing the QEI agenda at the EU level, so it's going to help sometime. Can you explain us why the industry overall, and particularly the end user you're representing on top of the industry vendors, are also, like Etienne, interested by the energetics of quantum tech?
Yeah, sure. I mean, just a quick introduction.
Oh, you can say also where you come from.
Yeah, because I don't come from quantum at all. My PhD is in biomedical engineering. I did my postdoc here, and I was applying fluid. It was fluid mechanics applied to the human body, so quite a bit off. But then became an assistant professor in England, and then Brexit happened. I decided to start my own company, and then afterwards joined Alice & Bohm, and that's when I started being into quantum. So not very linear path, but it's quite interesting to discover all that. And then what we know is the quantum companies that are emerging from the research are growing, and quantum cannot be a topic that can be carried by a single country, so it needs to happen at the European level. So I started engaging a lot at the European level, and so I joined the European Quantum Industry Consortium for Alice & Bohm 3 years ago. And last year I became the vice president, which means I am with my president and other vice president. We're the line of communication between the European Commission and the quantum industry. And in our role, we also represent quantum at these institutions called the EuroHPC. You might not know, but EuroHPC is a European institution that buys all of the supercalculators of Europe. They're based in Luxembourg. They might be the reason why the US left out Luxembourg out of the CHIP Act, so they're not allowed to buy American chips. And as a result, in that institutions, all of the HPC centers say, yeah, we have space for another, we need more computing power, our state can give that money and things like that. And some of the HPCs cannot join in. Europe sometimes says, I have money for the next supercalculators, and certain countries says, we don't have power anymore. We have the space, because the machines have been getting smaller and smaller, so they have the space, they just don't have the power anymore to install compute. And so they have those questions of, yeah, you guys are telling us the quantum computer is coming, what is it going to cost us in terms of energy? And especially now that we've moved into the FTQC, as you heard from a number of the speakers, like Mike was saying, there's a massive overhead attached to the error corrections. And so that's going to generate energy costs, and the HPC centers who know they're going to be the one installing these machines are asking, how many watts per qubit, how many watts per operation. And at the moment, we can't tell them. If you look in a classical computer, in the spec sheets, when those companies come, I mean, like IBM comes, they can tell them it's going to cost you that many
usually gigaflop
energy.
per watt, even though you can tweak the benchmarks, but that's the
it is in the spec sheets. It is one of the technical requirements, and we can't give them that at the moment. So that's why we think the message. And plus, Europe has the most expensive energy in the world. So if the quantum computer is developed to be super expensive also, for Europe, we're going to be penalized. So it makes sense that Europe carries the message of, you know, let's watch out for energy. Plus, we're the only one that are doing the Green Deal in the world. So let's be the ambassadors for safe, like low energy quantum.
Okay, so now we're going to switch to some of the vendors. I'm trying Pierre here first. You're the bad guy. I mean, you're the bad. I mean, you're the biggest one, the large one. I don't know how many computers you have. You install more than 60 QPUs, I think, so far, roughly. You're trying to set up your mic. Yeah. Open up the mic, but maybe we'll find a solution.
Oh, okay.
Debug.
I'm the stupid guy.
No, what I want to ask you seriously, Pierre, how the energetics of quantum computing became a topic at IBM? It was not direct. I mean, it took some time. So how did it become a real interesting topic, and how are you getting organized at the R&D level, not just? It's not a marketing thing.
And it is not only R&D level. And that's what I think we were discussing that with Camille during lunch. The fact is, it could seem bizarre, merci, maybe for some of you, but from a large corporation like us, the green stuff is part of the sustainability topic. And it's something that we took very seriously for many kind of reasons. The first kind of reason is because some country we operate, I think IBM, competitors love to position us as a US company. We operate in more than 165 countries in the world, and more than half of our employees are outside of the US. But still, we are a US-based headquarters company, and the reality of that is that we need to fit with the local regulations, and in a lot of countries, there are regulations that force you to explain what is your sustainability criteria. And quantum is not something that is outside of that. It's just one more line in our portfolio. And then if we, on the classical storage space, on the classical computing space, we are able to produce, and we must produce sustainability reports and energetic reports for our customers, that's the first reason. We need to do it for quantum. Second reason is a market advantage. It's a reality, maybe not today on quantum. I think the first objective of quantum will be first to build large-scale quantum systems, but maybe my other vendor there will say something else, but I doubt. But the reality is, first, it's also a place, and I remember in the classical space, I win on storage, some RFP, request for price and request for quotations, because of the energetic capabilities. As you mentioned, there are some places in the world where the power supply are not enough and are limited. Then we need to convey to that kind of resources, and there is no reason quantum will not potentially take advantage of energy to win new market. And third point is because of our employee. As I said, we operate in a large part of country of the world, and some of our employees are facing directly the climate change. Directly. And the reality is that if you do not address that seriously from an industrial standpoint, from a reality standpoint, you lose brain capabilities because people say, I don't want to work with a company that have absolutely no value and that don't care about the future. That's maybe seen from a strange point of view, but that's the reality. Then after that, quantum is organized as all the other business units. We need to explain how we will see the growing impact of energy for quantum, and we need to report to the sustainability offices, which is directly reported to the CEO, and which is asking questions which are maybe much more from a policymakers' question, because they are facing the policymakers every day. They are facing our customers every day, and they want to know some funny question. Can you plan your energy consumption in the future related to the quantum computing?
You gave us the reason, the motivation, but can you explain also the approach in R&D? So how do you look at this problem? Is the energetics of quantum computing a potential, let's say, quantum advantage source? Or is it a new energy consumption source that you have to tackle with? So how do you approach that? Who is working on that?
I cannot give you the details on how IBM Quantum is organized, but
I have the means to
I'm sorry, that's part.
Yes,
exactly. That's a good track, but I will not give you all the details.
I'll come back.
Let's imagine that there is some people working on systems/hardware, some people working on software, some people working on how do you make the link between both of them, quantum error correction and this kind of funny stuff.
Cryogenics, electronics, and so on.
That's where you come back to the systems. And I think that's what is funny is that every entity, groups, whatever, is it real groups or virtual groups, have an energetic view and have to take into account the energetic impact and have to take into account how they will optimize that. And at the end, there are also a kind of virtual group which is how do we integrate all of that to answer the question to the sustainability technical officer, which is asking us some funny chief sustainability officer, some fuzzy question. But from an organization standpoint, it's really, I say, it's systematic. After that, is it the objective of the main objective of everyone? I think sometimes no. I think the main objective of most of our people is to build the best quantum computer in the world. But then when you define best quantum computer of the world, energetics could be a way to be characterized as the best. Then it's a kind of trade-off.
You made a key figure of merit.
Key figure of merits comparison, yes.
Okay. No, Ariane, I would say you're the real person doing the real job as a scientist. First, can you tell us about your background a little bit? Yeah. Explain where you come from and what you do now at Quandela, and explain how the energetic topic was brought out within Quandela and how you're approaching that topic. And particularly what I would like you to describe is how you are managing the scientific aspect of energetics and how it may turn in some situations into an engineering problem. And what the skills are needed to do that in a, I would say, organized way in the company.
Okay, so my background is in physics. I did a PhD in mesoscopic physics and then 5 years of postdoc in quantum optics and quantum thermodynamics. So and it was theoretical physics. So I had never set foot in a lab before. And then I joined Quandela specifically to work on the energy consumption of the photonic devices developed at Quandela. The context of my job is because of the OECQ project that we talked about. So part of the project involved having people working full-time on the energy consumption of photonic devices at Quandela and Alice and Bob. But on the Quandela side, they decided to hire someone full-time and permanently for it. So that's how I got there. Then the other question is how do we combine? How does that happen in practice? Like, right? So it's tough, and I had to learn a lot of things along the way. So me personally, since I came from academic background, first of all discovering the industry world, and also I think what is the most challenging still today is to understand you need to do. There is research and fundamental science to be done to understand the energetic cost, but then you also have to very quickly adapt it to the real industry constraint, their design. So sometimes I feel there is this pressure that when you can ask questions of how would you optimize quantum error correction, and I can, with my background in stochastic thermodynamics, I can think, oh, there would be those nice trade-offs like uncertainty relations and so on. And if I had academic time scales, I know I would get nice results, but I know I need to be fast enough that I get results that make sense before we are done building the cryostat, for instance. Because then it's like, okay, it's nice, but you're too late. So it's hard to navigate. It needs to be a back and forth between doing the science, but also not going into too much details, because you need to understand you don't have the time for the details, and maybe it's not so relevant. And I think what's interesting in a structure like Quandela is a lot of people are like me, so in the sense background in theoretical physics. We're not trained as engineers, but we end up having to do the job of engineers sometimes. So if we're asked questions of what do you think would be the requirements for the cryogenic consumption of the next generation computer, these are computations that engineers typically would do, except we need also to have the insight from physicists because we know specifically how it works. So it's, yeah, you need to acquire new skills along the way. And day to day, it's just a lot of discussion with hardware teams, with experts from the outside world. But I would say at least the objective is clear, and the route to it is something you have to figure out along the way.
And I presume you have a lot of people involved, I mean, including Atocube, for example, for cryogenics,
yeah, exactly.
which is one of the partners you have in Germany. So it means you need to assemble a kind of transversal team with different backgrounds, scientific and engineering. And the orchestration works well. I mean, you're learning on the fly, I presume, on this kind of topic. And it's not the only one. Probably there's people working on algorithm design and other stuff. Yeah.
So I'm learning on the fly. The background I absolutely do not have is one in project management. And I think this is the main thing I discovered in the company, is how important it is as a job on its own. And we're lucky to have now very good project managers. And it's been, I was there before they arrived, and now I see the difference now that they're here. And it's it's a whole new story. So especially when you have transversal projects like that, not only within the company, but also with actors on the outside, proper project management is something that is essential. And it's very different than what you could do in academia. I have written research grants proposals before. It's a whole different story, because when you have different people involved, you need to know exactly what everyone could do and then align that. And so, but so in practice, yeah, this is how it happens. Like, it's transversal, and it's.
Thanks, Ariane. When I moderate such panel, I try to find symmetries or asymmetries. So I find a symmetry with Mert, because you're also a scientist. You became kind of a lead engineer in Quantware. So explain us, and take a mic, explain us the transition, and of course how with Quantware, where you are, you're dealing with energetics. So you are a bit like IBM in the superconducting qubit world. So how are you dealing with it? Because you're a mix of company, because you do chips implementing the qubits, but you also do enabling technologies like two paths. So you're
Indeed, yes.
in between. And what?
Indeed, yeah. Just not chips, but also two paths, but also the scaling architecture that I can touch upon. But maybe it's not so interesting for everyone, but still. Yeah. But maybe even before that, I just want to say that, I mean, I studied theoretical physics, like Ariane, and I did work on quantum thermodynamics and transport. That's how I know Roberts and Alexia. Then for a postdoc,
it's a small world.
Yeah, it's a small world indeed. Then I did something completely different during my postdoc. I worked on superconducting circuits, spin qubits, topological qubits. I get bored quite easily, and I switch topics a lot. But that gave me some perspective. Then at some point, maybe some of you can relate. I was trying to choose what I want to do with my career, and whether become a professor, stay in academia. But you have constraints, right? So it's a multi-objective optimization problem, I have to say. Then Quantware came to me. They said, okay, we have this cool project that we think is going to be very valuable, and do you want to lead that? And help us build the roadmap. And I said, okay, it looks challenging, because as I said, like Ariane, I was never in lab, so I always did theory, but I was going to run a theory plus applied physics group together with engineers and software engineers, whatnot. I said, okay, it's a challenge. Let's try to do that. It's device physics, so I work on, my team is working on readout chain of superconducting circuits and qubits. So this includes two paths. These are parametric amplifiers, quantum limited amplifiers. They are really amazing, if you ask me. There's too much physics waiting to be discovered. And actually, so it always comes back to this question of whether realizing a fault-tolerant quantum computer is just an engineering challenge. I don't think so, because this is how I see it. So there is a place where you want to be. That's the utility scale quantum computer or fault-tolerant quantum computer. And there are many ways to get there. One of them is maybe just pure engineering challenge where you scale things up and you solve engineering problems. The other one is, okay, what can I do with all my physics knowledge to allow, like, basically to think about the solution where it can give me some advantage. You know, whether it's a new type of device, whether it's a new type of physics. That's what I like thinking about, and that's what we do at Quantware. So that's why I'm lucky to lead a team that I'm currently leading. But it was a challenge because the team consists of many people, like measurement engineers, designers, fabrication people. But if you give enough time and if you're patient, then you can find a common language, and I think that's really important. Yeah, that's what I can say about
you remember Cécile mentioned that we miss figures of merit that are easy to use and to make comparisons. What are your key figures of merit, because you are at the component level more than the full system? So how do you view those figures of merit?
I think I'm biased, but I start from minimizing all the cost at the mixing chamber level. This is a bit too technical, but I really want to cut down the cost of running the qubit chip itself. And then there are many ways to do that. And which way is the best, it's unknown.
Can you elaborate?
So basically, you can offer many solutions to, let's say, input-output problem of any type of qubit modality, actually. And then what is the best way of doing that, whether it's an engineering challenge or physics problem, that you can understand along the way. And then I think there are many academic groups also working on that, right? So it's just an open question. And that's why I think also reading arXiv daily and then trying to figure out what others are doing is very important.
I'm curious about a specific component, the TUPA. Maybe you can explain what it is, a traveling wave parametric amplifier.
Yeah.
So you use that with Alice and Bob, by the way. So
I wanted to join in the energy tech opportunity, and what we see is in the assembly of the systems. Once you scale the entire system, 80% of the machine is control electronics, actually. And so that's where you're going to have a lot. We face the challenge that every time we're talking to states or potential end users, they're super freaked by the cryostats because they've never installed the cryostats, and they're like, oh wow, that's the thing that's going to use the whole energy. And when you do actually the count on it, this thing is on a closed loop, so it doesn't use that much. Everything goes into control electronics. So if we really want to have an impact, that's where we're going to have to tackle that. Especially, again, error corrections, tons of pulse control.
Electronics plus classical control, like Mike Vasmer explained this morning. Coming back, TUPA. It's just, I like the example because it's a small component. It doesn't consume a lot. There's just a tone pulse that control it. So how do you view the energetics of such a small component, and how is it important for the rest of the food chain?
Yeah, basically, TUPA is a traveling parametric amplifier, traveling wave parametric amplifier that consists of thousands of Josephson junctions, maybe hundreds or thousands, depends on the implementation. And it gives you a quantum limited amplification. What does it mean? It means that any type of amplifier adds noise, so this is unavoidable. And TUPAs and any other quantum limited amplifier adds minimal amount of noise, that is half of a photon, okay? So this is unavoidable, just like uncertainty principle, you have to have that. And whether you can get close to that is an engineering challenge, so I have to admit. But maybe there are some clever tricks that you can pull such that you minimize this, even though your fabrication doesn't change, let's say. And what is nice about TUPAs is that it's not just used for readout, but also some cool research, dark matter search and, squeeze generating entangled states and whatnot. So there are many, many, many people working on that and coming up with new ideas of realizing these devices. And I think also these devices are not just useful for amplification purposes, but also some other processes. Okay, I can speak about TUPAs for a long time, so let me not do that.
Yeah, but let's take an example. You can optimize the energy through minimizing the cabling, so you do frequency multiplexing, so you can improve the bandwidth. These are connected figures of merit. Is it the way you improve the
But I think even the device level, the circuit level, you can optimize your circuit in such a way that Hamiltonian level, in such a way that you can minimize the dissipation and you can make your amplifier more efficient.
Within the tupa, you mean?
Exactly,
Okay.
just on the theory level. And of course, when people were thinking about tupas first, they didn't think about this optimization. But as things are becoming more and more scarce, let's say because of the scaling up considerations, then you need to start thinking about these two. That's what I do, basically.
Seems cool.
Yeah, it is.
There is another symmetry, which is perfect, by the way, on the panel, is between Joseph and Marco F. Because Joseph, you are at Quobly. You have multiple hats because you were at EDF before. You were leading the OECQ project. Now you're managing partnerships at Quobly, if I'm not wrong, and applications. And it happens that Marco is more or less teaming up with Quobly somewhere. So explain what you both do and how you connect academic and industry vendor for the sake of improving energetics.
Yeah, so what we do at Quobly, so we, as the others, not big surprise, we are building a quantum computer, but based on silicon spin qubits, so on transistor. And yeah, for us, energy is a big one because, of course, at the end of the day, if we want to put 1 million qubit in one single cryostat, the challenge is not the place of it. The challenge is really energy, because the big topic for us is to have a powerful enough cryostat. So the big challenge for us is this one. Of course, if it's
and low power electronics, I presume, as well. Huh?
Yep, both of them. Yep. So to us, the energy is more like a challenge in the way that we scale the quantum computer at the end of the day. Because we have this target of building this 1 million qubit machine. Of course, we could do in another way, and we have competitors, not in this room. Just that
maybe next year.
Let's invite them. They have plenty of money, so you should. They plan to have a 100 megawatt quantum computer, and I'm pretty sure that they will do it, and I'm pretty sure that they will have customer. They will have customer on the defense side on some very niche applications, but for civilian usage, for EDF, for example, it's of new use. I'm not sure EDF will turn on 10% of a nuclear power plant to run some simulations. So the challenge is the benefit of working on energy are twofold for us. Get a usage that is dedicated to a civil usage of the quantum computer on scale. Speaking about the switch between industry, research, so we are a company which has been created by two different personas. So Maud Vinet, who went to IBM, by the way.
Long time ago, yeah.
A couple of years ago in your town.
Yeah, roughly. Yeah.
And another founder who came from National Research Agency in France, CNRS. So they compete together between the engineering part and the research part, so it's funny to see them. We are a company that is kind of strange in the quantum world because we just have 56% of PhDs, which is not that big in this area. So we have a lot of engineers working from a day to day on energy and trying to save energy on the control electronics, on all the parts. But it's these guys, these people comes from the semiconductor industry, by the way, which is kind of very efficient in terms of energy. And these are the people that works on energy, and we have people also working. Tristan has been working on the energy of silicon spin qubit with Rob in the room. So yeah,
you were involved in a project on cryogenics as well, with CNRS, Institut Néel, to create a crafted system, a specific system for you, at least for experimental experiments.
For now, if luckily enough, at the end of the day, it will scale also. But yeah, so cryogenics for us is the bigger of work on energy, and and the other one is really on the control electronics as the other
And
side.
usually when we talk about silicon qubits, you talk about the fact that it runs at a higher temp than superconducting qubits, or let's say half a Kelvin, roughly.
Yeah, the
And
summer.
so you have more cooling power, and you can do more. You can squeeze more electronics at different stage of the cryostat. So is that a real benefit from the energetics of the system? Is it adding up when you compute the total energy power, energy consumption?
Yeah, because at the end of the day, you will use the same cryostat. So if you manage to run it at 1 Kelvin or half a Kelvin, you have a benefit here. So we want to play on that, but of course we need to save energy, because 1 Kelvin inside the cryostat is very expensive outside. Yeah.
So I know that you hired one guy named Valentin Savin. He was from CEA, I think, and he's specialized in error correction. He was a kind of Mike Vasmer at CEA. And but you still work with INRIA and with Marco. So when do you choose as a company to work with high academics or work with academics who stay in the academic world? What's the decision-making process?
It's not our decision. It was his decision.
It's the people.
Yeah, it's a people decision. And so we had a period which might be. I think we had a period during which startups began to hire people from academia, which is good in the short term, but at the end of the day, academia doesn't train the people. Say we'll miss some students in a couple of years. So it tends to now we don't see that a lot in the US, because in the US, academia has a kind of prestige still. They do have a high bill. But here in Europe, it's not the same story. So we saw a brain drain from academia to the startups. Honestly, on the application side, I prefer to keep the academia in the lab, because they will provide me the students.
But in the case of energetics or stuff related to energetics, we know that there are not that many specialists in both ways. I mean, pure academics or even engineering. So does it mean that it makes sense to mutualize some of the work so that it can be shared across multiple companies? And that's where academics make sense as well, even from the pure economic standpoint.
So yeah, I totally agree with that, because.
But it requires some openness. That's the thing.
It requires some
not proprietary
openness.
designs.
And on the semiconductor industry, what we do often is that competitors, when innovation comes, competitors try to work together. So they are kind of co-competitors, because I do know that if they don't collaborate, at the end of the day, the innovation won't be delivered. And we are at this stage in quantum. So if we don't collaborate on some very costly part of the story, we'll all fail. Maybe not all, but most of us will fail.
So Marco, that's where you come in. So explain what you do per se. I mean, what's your research domain and your background? You come from the same ecosystem. You worked with Robert and Alexia as well. But now, what do you do at INRIA, and what's your personal goal as a researcher, and how you connect with Quobly?
So I have let's say two different roles. So one is indeed so that was supposed to be the topic of this panel, which was related to standardization. Unfortunately,
your role in the panel.
Because I'm responsible for IEEE effort to standardize the way energy consumption of quantum computer can be evaluated. But the thing is that there are some rules that when the as long as the standard has not been formally approved, you cannot go into details. And also, I'm academic. I got recruited at INRIA this year. And on the academic side, so I'm interested in various topics, but one of them is the energetics. And on this aspect, so indeed, I think that one of the role, in my opinion, of academia is to give, let's say, a different insight on the question. And because, it's making a complete realistic model of quantum computer is very challenging, and it needs really a lot of expertise, cryogenics, electronics, error correction. And there is something that academia can provide. It's another way to approach the problem, or to identify where we could gain in terms of consumption, like where we could gain significant energy consumption that will not come from, let's say, where industry will usually focus. So it probably bounces back a little bit on the talk I gave, but I think it's in line with us. So indeed, for instance, what you can do is to say, okay, I will have this quantum computer, which is a big machine, and I will try to reduce the consumption of the component inside. So that's one approach to the problem. But the thing is that you often have very complicated trade-off. For instance, let's say that I want to reduce the consumption that the electronics generating signal will cost. Often it will increase the noise on the hardware, because you need really engineering technological development to reduce the consumption of something without losing in performance. And for instance, one kind of approach to this problem is to think the problem in a more system manner, where, so basically, yeah, it's probably an academic way of seeing this, but essentially the question is, you have an amount of energy, how do you spend it so that your computer works well? So either, for instance, you indeed spend a lot of energy to generate very good signal, and then, for instance, you do a little bit of error correction, or you could say, I will spend less energy to make good signal, but I will actually spend this extra energy to do more error correction or more error mitigation. And so this kind of approach gives you a more system-level approach to the problem, which can, in some sense, be more efficient. Why? Because in many cases, it's a matter of better understanding how the computer behaves as a whole, which does not necessarily require new technological development, but a better understanding of how the different components are interconnected. And so, yeah, so to me, a contribution of academics is to provide approach to understand this problem. And I think there are many interesting questions, also perhaps a bit more fundamental, but essentially to understand indeed, the usual approach are often like, I really want to minimize, for instance, the amount of error correction I do. And from that, you can predict scalings. But if you ask indeed to minimize the energy consumption, which is not necessarily the same question for the reason I said, because minimizing the overhead of the code is not necessarily the more optimal one, you could have, for instance, different way on how energy scale. And so that's also an interesting academic question to understand how in this optimal energy scenario, energy consumption will scale with algorithm size. So, and in relation to Quobly, so actually, so this is very fresh, but we haven't concretely started working on, but it's a well-defined project. So the goal is indeed to realize that in many modalities, there are a lot of similarities. So I will give an example. So spin qubit superconducting, for instance, they require cryogenics, they require control electronics, and you have, and on the algorithm side, you can also have a lot of similarities. So there is a lot of work that can be, that can, up to some extent, be cross-platform. I'm not saying the whole model will be, but I'm saying a significant part of it can be. And so, for instance, with Quobly, indeed, the goal at the end of the day is to make a kind of, to release a kind of, that's the end goal, but to release a kind of open source energy simulator, so that we put example of spin qubit, but then after some platform could modify some specific equation in that and do their energy optimization, which I think will benefit to, because we don't have to reinvent the wheel each time, essentially. Yeah, and so, yeah, so I can complement, but I don't know.
Okay. So your mirror, Marco P, I try to distinguish them. So I find a way spin up, spin down, meaning one is open research and the other one is closed research. It's weird what I said, but explain what I said with the company where you're involved. Right. Because you're working with companies where it can't be that open. So that's why you're spin down.
Okay, thank you, Olivier. So, yes, so I'm here just to give an idea what this green quantum computing is. So it's a very young and small still spin-off of PQI. PQI itself is the Portuguese Quantum Institute. So it's a private, no-profit institution devoted to research and also science education and outreach. So it exists since few years. And also to give a bit more context, I myself also come from a completely academic background, like many of us here. Still, I am also a researcher in the University of Lisbon. PQI itself is a partnership between the University of Lisbon, in particular Instituto Superior Técnico, and two other partners, which are Deloitte, the consulting company, and the Portuguese Institute for Quality, which is the Meteorological National Institute. So, but it is focused on purely on research and outreach, and it's a no-profit organization. So, as Yasser showed yesterday in the talk, so we have begun since few years working both on a fundamental side on quantum thermodynamics, and then on a more, let's say, applied side on the energetics of quantum computing. We got into this purely from an academic, if you wish, quest, as an academic quest, and with the desire, with the hope to help contributing to the advancement of quantum computing. So, but as we were going along this, we realized that much of the experience we were gaining may be potentially useful to others, specifically to concrete cases, either vendors who are building quantum computers, or users who are planning, who are thinking of using or buying a quantum computer, and of course would like to understand, would like answers to the questions which were raised, like how much does it cost me in terms of energy and also money. So we thought that at some point we may be able to share this experience, and since that would not be possible with PQI because it's a no-profit organization, Green Quantum Computing was created as a spin-off, really with this more as an actual company. So this is it. Yeah.
By the way, I apologize, I made a mistake. There's a kind of anti-commuting problem with the name. It's Quantum Green Computing, the real name of the company.
I got confused myself.
I've got a very hard time figuring out in which order I should name this company. So it's green. It's not greenwashing, I hope. It's not greenwashing, I hope.
Not that I know.
No. No, but there's always this fear that the people who talk about energetics in quantum computing or whatever quantum energy are doing greenwashing. Pierre, explain me why it's not greenwashing.
No, but it's not greenwashing because at the end we live in a finite, let's say finite resource world. Then we need to handle that, and our customers live with that, and that's an economic advantage for them because energy is a cost. And then at the end, all our customers and user customers will go for, and I hope that you already heard about that, the total cost of ownership of something. I mean, maybe for the quantum world, that's something new because a lot of companies are very young. But from an industrial standpoint, that's not something new. When someone purchases an ASML system, they will look at how much energy the ASML system consumes to produce chip. That's the same from total. I mean, we are doing that with car day to day. We are used to that, and companies are doing the same stuff. Then it's absolutely not greenwashing. Greenwashing is when you try to hide something from the rest of the world and hiding from with a green facade and doing back stuff. But at the end, we will, from a vendor standpoint,
you can treat the numbers also.
Yeah, you can treat the numbers, but the numbers, if we are selling stuff to people that will install that and they will just look at the electricity counter. You know, we'll just put that. I put on the stuff. I look at how much I consume in 1 hour, and then I came back to IBM. You are just saying nothing, and that's not the reality. That's very easy to measure. And at the end, especially because energy is electricity for our world of computing, it's all of because of Etienne. Then at the end, we consume energy, we consume electricity. Then that's something which is very easy to measure. And then there is no greenwashing feasible. It will be fact-based. The question is maybe between now and in 10 years, 5 years, 3 years, depending on the roadmaps of the companies, where the maturity of the systems will evolve. there could be some green, let's say, advantage somewhere presented that is absolutely not the case, because you are talking about theoretical stuff that will never happen and will never be realized. That's the reality of the field.
Green embellishment.
Let's say that I'm not sure I'm able to say anything about the capabilities of my system, but then I will tweak a little my numbers to put my system in a way that will present positives to the field. That's the reality until we reach the real delivery of the system in the field, and then that's over. You have to face the customer, and I don't know for how you are planning that, guys, but you need to put fact sheet, technical sheet to customers. I mean, when Etienne is purchasing GPU servers or this kind of stuff for HPC, and I'm not a physicist, but I spent 20 years in the IT industry. I came from the HPC world, from the optimization code of HPC, and then the reality is that you need to put fact sheets on the table, and then you need to if I said you will consume 100 megawatt, I hope it will be less for this company. But if I say it's 100 kilowatt, it must be 100 kilowatt. At the end, it must be measured. That's energy is very easy. Let's say that on other parts which are not addressed today by the market, like reusability. How do you manage the defaults of the system, reutilize this kind of stuff, calibration, etc. That could be other part. But for the pure consumption of the system, that's very easy to measure.
Yeah, but it boils down to the standard we're working on at IEEE. To make sure we can compare the systems, we have to be able to compare the energy, but with having the same other criteria. Because if you compare a 100 logical qubit and 1 million operation machine with a 10 times or 100 times more, how do you compare? So it would force the industry to adopt a way to have a fair comparison system.
Yes, just a comment on that. In the HPC world, we have the Green 500 ranking now. It's a way to compare all these computers to each other. It has succeeded to the top 500, which is overall performance in terms of calculation. So they have been able to manage some benchmarks and so on. So maybe in quantum computing, we have to define the same thing.
Isn't that easier? Because if you look at the Green 500, you've got two criteria, I would say. One's in gigaflops, so that's the raw power, maybe on top of the data and memory that you have. And then you have the gigaflop per watt. Sometimes, if I remember well, Robert, the most efficient machine is not the largest one. The 60 gigaflop per watt, and the largest is about 40-something gigaflop per watt. So, but there's just two criteria. But if you take an FTQ system, it's more complicated because you've got at least 2 or 3 figures of merit. The circuit size, maybe, I don't know. It should be simple to make a fair comparison. Marco, what do you think about that?
Yeah, I think a big difference between quantum and classical is that in quantum, what is essentially difficult is to reach a given accuracy. And so, for instance, it does not, to me, doesn't really make sense to define a purely analog of flops per watt because it depends on the accuracy of the gates you want to do. And that's another figure of merit.
Which is the size of circuit, more or less. More or less.
Just to follow up on that, I think that when we will buy a quantum computer, we need something which is quite reliable and, as Pierre said, doing the job in a certain range for our applications in the right time with facts and figures which are validated, in fact. And, Green 500 is one, let's say, very simple criteria to make a ranking, but after that there are requirements and so on. And I'm quite happy that the community of quantum computing is taking the problem in advance, making this by design in the computers.
I remember we had a dream when we created the QEI 4 years ago that we would create a quantum Green 500. My remark back then is we may not have 500 systems to compare, but yes, it would make sense if we find a way to make the comparison. Why not? Okay, Cécile. Cécile?
But compared to the gigaflops, we have those figure of merits emerging. So the QOPS from the UK strategy So now Riverlane was pushing for very, very long time mega co-ops and giga co-ops. And now the machine that they're purchasing, the deadline is in next week for the purchase of a fault-tolerant quantum computer in the UK. And they were saying, we want to buy a machine that's going to be able to do giga quantum operations. Now the challenge is that they didn't define what is that operation? Which operation are we talking about? The fidelity of that operation.
What
so
share
obviously
of non-Clifford gates, by example?
exactly. Yeah, are we going to be doing?
It's a
Okay,
trick.
we can do like 1 million C nots, and that's it. It's not an algorithm, but we've done 6 million operation. Yeah, I think the community is slowly moving towards understanding that we're going to need those figure merits, but it's quite slow. Like just to give you an appreciation, you might know that we're doing the strategic research and industry agenda in Europe this year. A number of us are probably involved. I chair the chip industrialization chapter. What are the challenges for industrialization of the community? And you always have some people that say, oh, we need to focus on the components. We need to make the components better. And there is the question of, no, we're talking of a system. We need to look at the benchmark of the entire systems. And so you've got those two communities that are constantly fighting, saying, no, we just need to increase coherence time, we need to make sure that we get error rates on the QPU. But if the QPU is really good, but you're losing all of your noise inside of the cables and then in the control electronics, then your machine at the end doesn't work. Slowly, we're merging into a coherent community, but right now the transition is not easy. But it's a transition. I don't know how you felt. Like when I left academia and I moved into industry, I kind of felt like I underwent a genetic mutation. Like I literally had to change the mindset. What you were saying, like I don't have the maximum amount of time in front of me. I'm not doing an optimization to death, and I feel that's the entire community at the moment that's doing that.
By the way, I would like to come back to Ariane and Mert. What are the kind of scientific challenges that you would like to be addressed by academia to help you do your job? You have ideas about that? You already have collaborations, of course, but beyond the C2N and Modulab and so on.
So I think we need, what I would think of, and I'm not the only one sharing this opinion, there are also challenges because we've talked a lot about the hardware. There are also a lot of challenges from the algorithm side. Specifically understanding what is a quantum advantage fundamentally. We know that you have the violation of the Bell inequalities. We know that you have algorithms that use entanglement in some sense to be better, but we also know that maximizing entanglement does not mean maximizing the efficiency of your algorithm. And the connection between entanglement, non-locality, contextuality, and so on, and quantum advantage is still pretty blurry. And I think this is the type of question that should be addressed in academia because there are many very interesting routes to explore which startups might not have the time to do. So I think it's important also for startups to explore that, but this is where I think the connections to academia is really important because you have, because of all the tree of possibilities that we need to explore. So for me, that would be number one.
And Mert, for you? More
for
hardware
me,
stuff?
It's actually more what Marco described. So seeing this as a whole system and understanding all the trade-offs and how to actually think about the energy consumption from this point of view, I think this is extremely important and often overlooked. And when you focus on your own research so often, you lose sight of all the other things. And when you're trying to optimize something in your own fields, you basically miss the big picture. And I think this is really needed. Somebody with a fresh eye, being it a bit at a distance and taking a look at these things, just like what you guys do.
And Marco P, when you are in the company, you're the spin down, and then when you work the Marco P from PQI, you spin up. So you can ask the other one what you need. How do you do that?
Okay, I wouldn't really know, but because really most of the
unplanned questions,
of course. No, because as a matter of fact, our work has been completely on the pure research side so far. But it's like becoming a continuous transition, especially because our work itself is getting us involved, and we try to have discussions and connections with with many partners in industry to understand also what are how the hardware works, how the platforms works, how the not just the actual qubits works, but all the other apparatus supporting it. So I would say from the academic side, we can strive to understand as much as we can the physics mechanics and try to come up with better ones. And on the other side, we are making an effort, I mean, even personally, to understand all the more technical and engineering side of it, even down to the more financial aspects of them, which eventually also come into play. Yes, so.
And Marco F, you are on the academic side, but you make proposals. And what I know about what you do is you're interested in distributed quantum computing energetics as well. Is that a way to propose a new way to approach a new problem that's going to emerge progressively in the industry?
So I'm indeed interested in distributed quantum computing, but not yet from an energy perspective. But
soon,
at some point maybe. But yeah. So your question is about distributed.
No, the question is how you make proposals in the academia, but which is going to be useful for industry vendors as well.
So yeah, I can give different examples. So so indeed, to me, it's very important to have the global view, because often, sometimes if you want to optimize one thing, it's either completely negligible in the big picture, or you do a local optimization that improves this but degrades something else. So if you do not have the whole system vision, you cannot really understand the problem. So for me, that's the first part. And then the second aspect is that it's important also, so that's really a work to do on the research side, but one argument that to me is is a bit incorrect is to say, oh, but this cost that I spend at the quantum scale, like very close to the chip, it's negligible, so I don't care. So this can be misleading, because often what happens is that you have a very tiny cost that is spent on your hardware, but for a bunch of practical reasons, this cost is then amplified by several order of magnitude at the classical scale. So if you divide by 10, for instance, the energy that your hardware consumes at the very quantum scale, maybe this cost is negligible, but it's not the thing that matters, because you will multiply this by the huge factor that at the end can... But the thing is that it's not always the case. Sometimes you have something small that if you reduce it, it will not matter in the big picture. So this is why there is a need to understand the whole vision to precisely identify the important research question. And another thing that is related is that, so okay, it bounces back a lot on the talk I gave, but it's relevant for this discussion. So what essentially costs energy when you do a computation is to fight the noise. So if you do not understand...
In FTQC.
But even in NISC, everywhere. If you don't care about the noise, no cryogenics, no high fidelity signal generation, no error mitigation, your cost is very low. So the thing is that we also need to better understand. If you better understand the noise, you have clue on how to reduce consumption, even if you do not directly talk about energy. So that's another example.
Will, you want to comment on that? Yeah, go.
I think that's, I mean, totally agree with Marco. We need to have a systemical view of this problem. It is a very hard problem. As Ariane said, it includes the software and it includes the algorithm part, because something that could have a very small, tiny impact on the hardware could have a tremendous impact on the overall system when you do thousands, billions of gates that will absolutely multiplication effect, and in the reverse side, any optimization, if you divide, look at the number of gates that was the evolution of gates for the well-known Shor algorithm in the last 10 years. I think it's better than every optimization from an energetical standpoint that all the community of quantum computing in the field have done, because they just divided by dozens of millions, the numbers of gates, it
depends.
Dozens, let's say dozens, thousands of gates, of time, the number of gates needed, and that's more than all of what we can do at an hardware level, pure hardware level. That's clear. Then I would agree that it's a systematical loops, and we need to be organized on that. And then comes the link with the academics, which is very hard, is that because academics, generally, they are less, some people are doing systemic research, but academics are less organized.
System integration.
System integration, but some people are working on a systemical research and how a global system will impact on the others, and what Marco said on the trade-offs. But the difficulty is how do we map, and after that is also how do you protect your IP, because the systems itself is quite protected.
I have a question for Etienne and Cécile. I don't think we addressed that question in the last panel. What can we learn from what happened with AI? Because when we created the QEI, I remember we said, oh, the AI was unplanned energy consumption surge, and it was even before the LLM surge. When we started the QEI, it was in summer 22, and ChatGPT became popular late 22. So it changed the landscape. We have huge data centers being deployed with gigawatts of power, potentially for at least for inferences, but even for training. So to be blunt, what kind of mistakes may have been done in this world at the R&D level, at the deployment level, and what can the quantum computing industry can avoid, can make to avoid some of the mistakes that may have been done, if there were mistakes. I'm not sure about the mistakes, but what are, Joseph, you wanted to respond on that? Yeah, you move the mic. You move the mic first.
So the AI story is hopefully not, but for now it's very different because AI is a massive usage. I'm not sure we'll have a massive usage of this category for quantum. I hope to be wrong, but as far as I know, today it's not the story. Besides, usually we improved computational power at first. It was the only figure of merit, as you mentioned. It was the only indicator that we worked on for the last couple of years. And if we look at the Green 500, it came out, I think, 16 years after the top 500. So usually we speak about energy a long time after the innovation. Regarding quantum, it's kind of different because energy is very critical for the whole industry. It's not a nice to have. It's really critical. It's kind of existential for most of the companies. So maybe we'll miss these mistakes, and we are here to put energy at the center of the discussion for a simple reason. It's not a greenwashing. It's just because if we don't do that, we won't exist.
Yeah, but interestingly, the top 500 and even the Green 500 is mostly considering scientific computers, if I'm not wrong, not the data centers which are using doing LLM for consumers or the cloud for Amazon and Microsoft and others.
Yes, all right.
So it's a different use case.
The use cases and the benchmarks are designed to solve scientific problems. And I'm not an expert on that. Question is difficult, but to me, AI and GPU farms, it's like a brute force and let's say always the same type of operations and the same type of runs and so on. And it's radically different from HPC and complex algorithm and so on. So difficult to compare. And yes, it is an opportunity to use GPUs, and
we have equivalent.
It is an enabler.
What Pierre mentioned about Shor algorithm, resource estimates, which have changed over time, it's the equivalent of DeepSeek compared to ChatGPT, which consumes less. I don't know about the performance because there are many ways to compare LLMs, but it seems that there are parallel phenomena happening in those two worlds. But let's say I'm a company and I'm creating a chip that runs matrix multiplications. That's what we do when we do LLMs. And I have a power that's 1/10 or 1/100th of NVIDIA GPU. Can I be successful?
I'm going to be
I'm doing the same stuff.
I'm going to be a little bit pessimistic, in which the Green Deal existed before AI, and as soon as AI came, we didn't care anymore how much energy they were using. And it's not a question anymore. Everybody just wants to have compute power. And I wonder if we're going to see the same thing in quantum. I mean, we have to accept that some of the biggest machines being built right now in quantum, the psi-quantum machines, nobody's questioning their energy use. Huh?
Yes, I do.
Apart the QEI, and they're still selling those machines, and they're crazy expensive.
They don't sell it, by the way.
Yeah, but
they will deploy it on their own sites.
But they're still building. They're still building like a bunch of buildings, and
they will try to sell it. Okay,
and the thing,
$1 billion.
The thing I'm seeing is that if you're strategic enough, you're going to be forgiven on your energy use, unfortunately. And Europe, the reason why we're carrying this message is because we're energy starved. But a lot of other countries are not energy starved. A lot of other regions in the world are not. So we do that also because it's in our interest. And then it turns out that it's also great for the planet. So I am quite happy carrying this message.
Yeah, the same story with LLMs is that some people don't care about the energy because they look at the return on investment. So they think about the value. There's a company we mentioned, which I won't mention, which said, we don't care, it costs a lot. We will cure cancer. It's stupid, but it's a way to say the value is going to be so enormous that we don't care about the cost. So are you saying that to your customers?
No, I'm not saying that to the customers because once again, we operate in many countries and let's say that when you operate with Orange Caraïbes, and that they have a limited number of power for the Caribbean island, you need to deal with the limited amount of power for Orange Caraïbes when you sell storage. And then that's the reality, fact-based. That's the same for some, I don't know, Liechtenstein, Luxembourg, or other place in the world where there are limited size of energy because of the grid and whatever. And I think you're right. For Europe, that's crucial because instead of France with the nuclear energy, we are clearly in a depth of energy in Europe. Saying that, after that, let's not be too aggressive versus the AI world. Look at what happened with the TPU. Look at what happened with the specialized engine, where, as you said, Marco, on the quantum field, I think it's the same on the classical field, they moved from fixed 32 precision stuff to diminishing the precision, being able to do calculation with less precision to increase the speed of the inference, but also decrease by a massive amount the impact. And I know that IBM, Google, Intel, AWS at least are working on specific inference chip, are selling specific inference chip that are 10 times better in terms of energy cost versus the GPU. Then AI, I think the issue we have is there is that, as Etienne said, is the consumer model. Then if you do the math, it impacts almost everyone on Earth right now through this funny stuff, and then the demultiplication is terrible. That we were having the discussion on the PQC, for example. I think from the quantum standpoint, maybe quantum computing is not the place where we should invest the most. I think we already discussed that, and I think PQC for post-quantum cryptography should be maybe the place where we should put the more efforts if we want really to diminish the energy impact of quantum, because we will be using PQC everywhere. Then a 5% increase, let's say not increase, diminishing of energy consumption of every PQC algorithm will have much more impact than 100% on just the system that we will sell.
Did you get the numbers?
I don't know. I need to do the numbers. Olivier, we discussed that 2 weeks ago.
I saw a couple of papers. It's kind of, we got to check the numbers.
but I think that's a very interesting question. I mean, from a quantum impact, I don't know. That's a very open question.
We have a couple of minutes left. The last one question I would like to ask you is the one that was asked yesterday in the discussions, and some of you were not there yet, I think, Cécile. How the QEI can help as an object, which is a kind of UFO in this world. The QEI, the community that's here, how can it help to craft a message and to organize, maybe, kind of not organize, but incentivize some forms of science and engineering?
So
Cécile.
I've got a strong opinion, and that's why I keep on putting you up there at the European Commission, because they're building the Quantum Act. So I don't know if you're aware, but the European Commission is at the moment drafting what's called the Quantum Act. Last year, they came up with their quantum strategy, which means, okay, this is the ambition we have for Europe. The Quantum Act this is how we're going to get to that. That's why I grabbed Olivier and I was like, we need to make sure there's an energy aspect to the Quantum Act, because otherwise they're going to be pushing for actions and they're not going to take into consideration the energy. But as a result, all of the work that you're doing, all of the excellent presentations that we've seen, need to make sense at the system level, because they're right now deciding which are the benchmarks of the quantum computer, and like we were saying, we need those figure of merits. So please, if you can, we've been saying, please think at the system level, whatever gains or advantages and optimization you're doing on energy, tell us how it replicates at the system level, because that's the information we need to push for the member states and the European Commission.
Any other opinion on what the QEI should do, or should be on as an object type?
So one example of success, I'd say, is OSCQ, which put together end users with two different startups, two different competitors. And people from QEI managed to coordinate the submission of this project. We need coordination at this stage. So we need coordination between competitors, between academia, and we need QEI to be loudy when it comes to speaking with regulatory agencies, because if you guys have the knowledge of the general knowledge of it, you will be the ones that are
We should
relevant.
create a OECQ SDK, so that maybe in Asia, in Singapore, in the US, somebody creates a similar project with local vendors and local industry users, maybe. It's probably some work, but
you have our
documenting what
support.
you do. Ariane, could you document everything? No. It's
I was wondering what is an SDK.
Oh, a software development kit. It's a nickname for a kit that is used by other developers. It's a paradigm. If you were in the silicon business, you would say it's a PDK. It's a different naming. A product development kit. Is that it's the specs of how do you manufacture your silicons. So a kit.
So I fully agree with you, Joseph, on that, and probably QEI has to carry an end-to-end approach. And so I think science is in the room. It's a lot of work done on this side. Maybe on the end-user side, I'm the only one in the room, so probably we have
not
to...
the last one, we hope.
I hope so. But probably we have to also to carry the message and to get different point of view of in the future. How do we operate by a quantum computer? Maybe use a quantum through the cloud and so on, and how we get the good guarantee of everything is let's say green.
Mert and Marco spin down. No, sorry, Marco P. You are a bit newcomers in this ecosystem. So, what's your thought about it? How this community can help? Develop the messaging and the science and engineering around energetics. If you have some views on that, you were there yesterday when we had the discussion. Yeah, we were together, by the way.
Well, one concrete and quick answer is really the effort that we are making on the IEEE front. So, because that makes it something clear, public, and as much as we can, well defined, at least as a starting point. And even beyond what the technicality of what is written there, I think it already poses the problem. So that for many people, even policymakers, this might have got completely off the radar. At least they might be aware that this is a concern that exists. Yes, and yeah.
By the way, we will have to define the semantics, because there's going to be questions about the metrics we were discussing. We have some ways to evaluate the energetics. That's part of the work Marco is leading. Then people will ask us about benchmarking, which is another ploy. So we will have to build a messaging around that. Mert, you want to add something?
As an academic switching to industry, I would like to have QEI actually bridging the gap. Maybe this is just a reformulation of what everybody said. To help industry to formulate the problems they're facing in such a way that the academics can understand and work on. So I think there are many, many overlaps that we just don't know how to, or we have few people who can formulate this, take an overview from, let's say, distant. Maybe QEI can help with that, be the bridge.
But like we say in movies, we are QEI. it's not a single person. So it's everybody here in the room, those who are not in the room as well. And Ariane, you wanted to say something?
Yeah, I have it's not exactly about the role of the QEI. I was just thinking about what you were mentioning about the European Commission writing the Quantum Act. I have a very naive question. Who are the people doing that? I mean, how far of the expertise are there? No, because I know it's also it was also a problem with AI. It's a problem with data privacy online, that policymakers are often very far away from the technical details. And so, for instance, you're saying we need benchmarks now. We also are working on the benchmarks. We understand it's a hard question. So if there are people writing down an act now believing that those benchmarks exist, I wonder who they are. That's all.
Yeah, it took me forever to understand who was doing what in there. So if you understand a little bit the European Commission, there's different ministries. They're called DGs. Quantum belongs in DG Connect, which is the ministry that takes care of digital technologies. And then there's a head of quantum that takes care of writing the Quantum Act. They did realize that they're not super experts in quantum, so they created literally 3 weeks ago the Quantum Assessment Board, of which Olivier is part of.
Quantum Computing Assessment Board. Yeah, it was a couple of weeks ago.
Yeah, and so they're creating a bunch of committees of experts. What we're challenging as the Quantum Industry Consortium is that to limit the conflict of interest, those committees are fully academic. And then we're seeing the issue, then it's not the role of the academics to build the systems and sell them. It's not their job. But we're missing, as a result, a voice, and which is why we're doing as Quick. We're trying to engage with those academics to explain to them, business models. If you put crazy rules, we're just all gonna die. And so, yeah, there's a whole community of actors that are engaging with the European Commissions. And to be fair, in Euro HPC, remember that entity that I said by all of the super great quantum computer, 2 weeks, at the last governing board I was there, they ask all of the member states, you need to have a representative specifically on quantum. So now all of the countries, the 27 countries of Europe plus UK plus
Switzerland, probably.
Switzerland, Israel, and I think Turkey is there. I can't remember. But they now have to have a specific quantum representative because they take care seriously. And that was a big win because they kind of said, you have to be in the room to discuss quantum.
To comfort you, Ariane, it's not the Illuminati from Da Vinci Code. That's these are people.
But I may have a question. Who could have asked the same questions than Ariane in the room?
You all knew.
You all knew who was working there.
You could ask a question about the US, because the US, it's the same complication. There are a lot of bodies. Between the DoD.
Except they put the industry in there.
Yes, maybe more. Yeah, you're right. Yeah, maybe more. They don't fear conflict of interest in the current administration, I think.
But because the US, the investment in research and development in the US is mostly driven by the private investors, and not, as we do in Europe, by the public investors. I think that's, let's compare fact-based the amount of money spent by the large corporation in the US and by the amount of money spent by the large corporation in the EU, and I'm not, let's say, challenging the fact that it's good or not. is fact-based stuff. Is that, and that we are very lucky on that in Europe, in my point of view, because that's the difference, and that's why we can still have a lot of that. But that's also their position. But after that, it's the same mess.
Cécile, you have the last word because you have to leave room
sorry,
if I'm not wrong.
So just to reassure you,
Yeah.
just to reassure you on quantum, we are trying to explain that we need more of a different model to push the kind of capital that needs to be raised. And yesterday I was literally sitting down with some of the policymakers, and a lot of them were complaining, oh, yeah, some of our biggest scale-ups are now going public, but it's really not good. They're doing it on the US market. And we're like, yeah, because if you list yourself on NASDAQ, you're going to make 100, 1,000, almost 1 million times more than if you list yourself on Euronext. What are you guys doing to make sure we have a European NASDAQ? You can't blame the industry for trying to make money.
Okay, we are done. I hope it was interesting for you. Well, oh yes, we didn't take questions for the room. I'm stupid. Yeah, I forgot that. Yep, go.
So during the coffee break, make yourselves available.
Yes. No. No, but since it's a break, let's take 1 or 2 questions, burning questions. Maybe you have some. I forgot. Sorry, I managed to have these folks say interesting things, but you may have questions. Any question to those guys? No? You want really the break. You were courageous. 1.5 hours listening to 9 people. It's a lot of courage. Thank you very much.